Okay, this is the next problem, right? So this is s to the 6 plus 4 s to the 5 plus 3 into s to the 4 minus 16s square minus 64s minus 48 equal to 0. 6s to 4s to 5, 3s to the 4 minus 16s square minus 64s minus 48 equal to 0. All right. So our intention is to find out whether this system is stable or not, right? So we'll start solving in a very normal fashion. Okay, so s to the 6, s to the 5, 4 s cube, s square, s to the 1, s to the 0. So this is 1, 4, 3. So there is no s to the power 3, so this becomes 0. Okay, then minus 16 minus 64 minus 48 and 0. All right, now please calculate the values and we'll see under what condition we may face a new special case. 0 0 minus 48 below this, right? So this is first number is 0. How is that? See, 4 into 3 minus 0 by 4, so it should be 3, I guess. Can you check once? Okay. Huh. Then, yeah, please proceed. This is a special case when the complete row becomes equal to 0. All right. So what we do now, even if you take an epsilon for the first value, it's still the same, right? So we correct. So because of that, what we are going to do now is see we have a valid row above this, correct? So we had a special case here. Above this, we have a valid row, right? That has actually valid entries. So from that, we try to derive this row, because you see there is this term. If you try to convert this into an equation, this is 3 times s to the 4, right? We have a term. So if you differentiate that, we get a term which contains cube. So from always, whenever the row, complete row becomes equal to 0, you need to write the equation for the row above that. So that will be 3 into s to the power 4. Next, you see there is a 0, right? If it is s to the 4, this is s to the 3. So this 0 is corresponding to s to the power 2. This is corresponding to s to the 1, right? And so on. So we have to consider the terms like this. So 3s to the 4 plus 0s square minus 48 into s to the power 0. S to the power 0 is 1. So we have this equation. Now you differentiate this, right? So I have to perform the d by ds of that, which means what you are going to get this now. So this is 12 s cube plus 0 plus 0. So it's simply 12 s cube. So the corresponding to s cube, I can actually remove this complete row now. I don't have to use this. You write whatever is here. S cube term will come here, that is 12. Right? 0 into s to the power 1. So this is 0. 0 into, right? All other values are zeros. Okay, so you write this and now you proceed. Now you use this like this and proceed. Yes, sure. So 0 minus 48, right? The next minus 48, 0, 0. So now we actually face the previous special case, right? So of the first number being equal to 0. So what's the solution now? Whenever this becomes equal to 0, I have to replace this with a epsilon, right? Here the epsilon is, right, positive, because all the values above this are positive, right? So I have to consider the values above this particular row, they are positive, so I make epsilon also positive. Huh. I repeat. So one, now we see that the s square row becomes equal to 0 minus 48, 0 and 0. right? So this is actually the first special case we considered, right? So the first element of the row becoming equal to 0. So as soon as we see that, our solution is that replacing that with a epsilon value, right? Epsilon is very close to 0. You can make it positive or negative, but in this case we are going to make it positive because sorry, all the values above the 0 are positive. So we don't want to introduce a sign change by making epsilon as negative. Right. So we'll calculate the next value by in terms of epsilon. Uh, minus, it's positive, I guess. Just check now. 0 into, sorry, epsilon into 0 is 0. Minus 12 into minus 48. So plus positive. Just check. So this is not minus 12. It's actually epsilon into 0 minus 12 into minus 48, right? Because of that, we get a negative quantity becoming positive now, right? So this is 576 by epsilon, okay? 0, 0, all right. So 48 comes, I guess, minus 48. So we have to find out the total sign changes now. Yeah, sure. Which means there is one pole on the right hand side of the S-plane and the system is unstable. Okay, then let's go to another question now. All right. This is s to the 6 plus s to the 5 plus 4 s to the 4 6 s cubed plus 5s squared plus 3s plus 2 equal to 0. Right. So we'll draw the Routh table. One, 3, 4, 6, 5, 3, 2, and 0. 3, 2, 0. Okay. Yeah, please proceed. The next 2, 4, 12 and 0. The 12, just check the 12 once because you are dividing by 3, right? 3 into 2. No, this is 3 into 2. That's a 4. I'm talking about this 12. 3 into 2 by 3. 2, right? Okay, okay. All right. That's 2, right? Okay. Right. 12 minus 12 by 2. So 0, right? Okay. 2 into 6. Mhm. Mhm. Okay. So we got all zeros. So consider the equation above this. That is 2 times s to the 4 plus 4 times s square plus 2 equal to 0. So this is the equation. Differentiate. Actually, yeah, so you can actually directly simplify this if possible, right? Because there is a 2 common throughout in the above equation. I can write it as s to the 4 plus 2s squared plus 1 equal to 0. And then I differentiate. Okay, so differentiation. This is s to the last one. Okay, and now 1 second. 4s square, because see, this is power 4, this is power 3, then the power 2, power 1, power 0. Okay, no, so right now I didn't perform the differentiation. I simply took the 2 common, right, and cancel that. So yeah, now we'll differentiate, or when you do the differentiation then you take the common out. Okay, that's fine. So we get the same answer, I guess. So we have 4s cube plus this is 4s equal to 0. So instead of this, right, instead of using this, right, we use the updated values. So what's that? This is 4s cube, 4s cube, 4s square, 4s 0 0. Okay, so now use these new values to calculate the next rows. All right. Okay, once again we get our zeros. So that means I'll write the equation above this, right? So this is 2s square plus this is 2. 2s square plus 2 equals to 0. So differentiate. 4s equals, so instead of using these, we are going to replace them. We'll replace them as 4 followed by 3 zeros. So 4 into 2 minus 0 by 4, it's 2, I guess. 2, 0. So now when you verify this, you can see that there's no sign change, so the system is stable. Alright. This is one type of special case. Now we go to the different types of questions wherein we can see that some unknown values, if you don't know what is the gain of the system that has to be substituted so that the system becomes stable, right? So we can find that. All right, so this is the question in a unity feedback system. G of s is equal to k over s into, okay, this is 1 plus 0.4s 1 plus, okay, now the question is find the range of k for which the system is stable, okay, for which the system is stable. Okay, also we'll add a question here also. Yeah, correct. So it is 1 plus s tau format, so it's a time constant format, right? So also find the k value at marginal stability and find the frequency of sustained oscillations. Okay, so this is a question. This can be added up. So I wanted to solve everything together. Right, so let's now you see that it's given as a unity feedback system, so I can directly write what is the characteristic equation, because we are interested in only the characteristic equation, right? So I don't want to, you don't have to write the transfer function at all, right? Directly write the denominator of the transfer function, which is 1 plus g into h equal to 0. So it's given as a unity feedback, so definitely the h is 1, h of s is 1. Correct. So we'll write this is 1 plus the g is given as k over, this is s into okay, this is the other format, so 1 plus 0.4s 1 plus 0.25s, okay, g into h equal to 0. Okay, so now we'll multiply the denominator to the left hand side. So this implies I just have to perform this s into 1 plus 0.4s 1 plus 0.25s plus k whole divided by s into, this is 1 plus 0.4s 1 plus 0.25s equals to 0. Anyway, the denominator is going to get cancelled because that's going to get multiplied to the other side. So just simplify the this part. Okay, simplify this and give me the answer. So plus k will be writing. Yeah, simply you multiply and get the simplified format. Yeah, sure. You multiply. Okay, what you can do is you multiply the bigger terms first. This and this you multiply. Later on you multiply with this. Okay, so this is 0.1 s cube uh, plus s. So there is a k in the numerator, so we'll add that. Plus k equal to 0. So this is the uh, characteristic equation. Now, fine. Let's we need to find the range of k for which this system is stable, right? So what we are going to do now, we'll write the RH table. So this is s cubed, s squared, s to the 1 and s to the 0. 0.1, 0.65, coefficient of s is equal to 1 and the constant is equal to k, right? So let's go with the calculation of s to the 1, the coefficient, with the k as it is. We'll keep the k, right? It might appear in the result. All right, no. 0.65 minus 0.1 times 1 into k whole divided by. So this is k. All right. Now the question says that the system needs to be stable, correct? in the question it is mentioned that find the range of k such a way that the system is stable, right? Which indicates that uh, no, what is the condition for stability using RH? There should not be any sign change. That's all. Correct. So when we say that there is no sign change, right? It means all the values in the first column must be positive. Right. So now you see for what values this k is positive, any value k greater than 0. Correct. So this indicates that the k value is definitely greater than 0. Right. Okay. Now anyway, this is positive, this is positive. Under what condition this is positive, I need to trace out. Okay, so this implies that the 0.65 minus 0.1 into k must be greater than 0. Okay, now what we can do here is, right, this itself will elaborate and will calculate like this. So this implies, now take the 0.65 to other side, or you can take the 0.1k to the other side. So 0.65, right, must be greater than 0.1k. So it means k should be less than 0.65 by 0.1, that is equal to 6.5. So the highest value of k is 6.5, lowest value is 0. So the range of k for which the system is stable is this. This is the answer to the first part. One of the row is going to give you the lowest value of k, other row will give you the highest value. Okay, the next part, in order to answer the next part, right, it says that whenever you are finding the marginal value, so what is the marginal value of k is the question. Marginal value is the highest value of k for which the system, right, is marginally stable. Whenever it is equal to 6.5, system is marginally stable, right? So we'll answer that part now. It's like this. So k marginal is equal to 6.5. That is because it is the highest value we found. Now, in order to find the frequency, right? In order to find the frequency of oscillation at k marginal, right? We are expecting at least two roots, correct? At least two roots such a way that we satisfy the following condition, and the equation should look like this. So if this is the real, or I can write sigma, this is j omega. Whenever the k marginal comes into picture, you have two roots on the y-axis, imaginary axis, correct? So this is the condition at that case. So I need to find out plus j omega whatever marginal, or I can call omega 1 minus j omega 1. I have to get this. This is the s value, right? Can be s1 and s2. So I need to find two roots, right? So I have to look at the table and I have to extract that part from the equation, from the table, where I can get an equation which generates two roots. So at least two roots can be generated by a square line. So equation, right? So this implies from the table I am writing. So what is the coefficient? Coefficient is 0 point into s square plus the marginal value, correct? So plus I'll write the equation once. This is k marginal equal to 0. So let's substitute 0.65 s square. Okay, so plus 6.5 is equal to 0. So s square is equal to minus of 6.5 divided by 0.65. So this comes to be minus 10. So under this condition, calculate s. S is equal to plus or minus j will come because it's minus 10. So root of 10 plus or minus j, find root 10. J 3.162. So it actually I have to compare this with j omega. All right, plus or minus j omega. This implies the frequency of oscillation I can directly find it is omega itself. Right, so we can see that the omega value is this is equal to 3.162 radian per second. Okay, let's go to the next question based on the same concept. This is s to the 4 plus 22 s cube plus 10 s square plus s plus k is equal to 0. Question remains same. Find the range of k for which the system is stable, and also find the marginal value of k and the frequency of sustained oscillations. We'll start in the same format, like we have to start with the RH criteria to get this. So s to the 4, s cube, s square, s to the 1, s to the 0. 122, 10, 1, k, 0. Uh, so what's this a square coefficient? 18.95, 22 into 10, 220. So that is 219 divided 18 square. This is 10, sorry. Okay, this is hmm. Okay, 9.95. Sure. Yes. Yes, yes, yes. Correct. Now, the first three values are positive, so we expect if the system has to be stable, everything should be positive. So, tracing that out, we find that this k should be greater than 0. From the last line, it has to be positive now. So, because of that, we can simply say that this has to be positive. So, k is greater than 0 will come to that. At the same time, from the above equation, we can find that 9.95 minus 22k also should be greater than 0. Only under this condition it is positive. That means what is the value of k now? 9.95 is equal to 22k. So k, yeah, sure. Please take your time. No problem. So k has to be less than. Okay, this is equal to 0.45. So now we can directly write the range of k for which the system is stable, right? So range of k is 0 less than k less than 0.45. So this gives what is the marginal value, right? K marginal is nothing but 0.45. So once we have this, what is our next objective? We want to find out the frequency value. So how do you find out the frequency? Hmm. Right. So for the that correct. Hmm. Right. So we have to write an equation. Auxiliary equation can be written. So auxiliary equation for s square will write. So 9.95 into s square plus 0.45 is equal to 0. So s square is equal to minus of 0.45 by 9.95. The value of square is equal to no, it should be lesser than 0, I guess. Just check now. It's negative minus. Okay, minus 0.045, right? That means s is equal to plus or minus j times root of 0.045. Equating this with omega, we'll find that the oscillation frequency of oscillations for this should be 0.212 radian. Yes, yes. Whenever we have s equal to j omega, it means no real part. So the root s is present on the y-axis. So as soon as we have this, we can directly write that. Okay, this is the required answer. Correct, correct. Next question. Okay, now there is another special type of question for this. Okay, find the number of poles on the imaginary axis of a system with the characteristic equation as follows. Okay, so that is s to the 6 plus 2 s to the 5 plus 8 s to the 4 plus 12 s cubed plus 20 s squared plus 16s plus 16 equal to 0. Right? Please try to answer this. Now the question is that find the number of poles on the imaginary axis. Right? So you have to give the answer like maybe, yeah, you, yes, correct. Right, right. Very similar way you can answer. Right? So you solve and give me the answer how many poles you found that they are present on the y-axis. Right? Actually, there are 6 poles out of which how many poles are on the y-axis is the question. Okay. This is 2, 12, 16, 0. Yes. Okay. S cube, it should be uh, 2 into that. So, so okay, so this becomes 8, 24, 0, 0. Okay, yeah. 6, then 16, right? Minus 0 by 8. So this is so now which equation you are going to use? How you can find out the number of poles? So all the six cannot be present on the y-axis. Okay, if that is the case, you will never get an equation like this. Okay, if all the six are imaginary, right, maybe you will get some s to the 6 plus a number like plus 35 possible equal to 0. Then only you get s to the 6 is equal to imaginary, right? This goes to the other side, all the six roots are imaginary, right? That's not the case. Correct. So that's not a case here. So six roots cannot be right present. So when six is not there, if at all a root is present on the y-axis, its conjugate should also exist. So I there is no meaning in finding using these. Six is ruled out. I eliminate. Five is ruled out because five means it does not satisfy the complex conjugate property. Correct. So 5 is ruled out, 2 3 is ruled out, 1 is ruled out. Anyway, yes, the 0 is also ruled out. So now I have a chance saying that either two roots are there or four roots are there. Both are possible. So you always try to eliminate whichever is not suitable to the given question and start from the highest one. So now there is a possibility of 4 present on the y-axis. So you write an equation corresponding to that. So what is this? This is 2 into s to the 4 plus 12 s square plus 16 being equal to 0. Yeah, sure, sure. Let me know once you are done till here, then we'll proceed. Highest one will start writing, right? Anyway, if you get an answer here, s to the 4, if you solve, either you get all the 4 roots present or the 2 roots present, right? So I don't have to start solving from the lower one, you can go to the highest one. So now s to the 4 means, right, I have to get 4 different roots. Again, directly there is no method, we'll make a substitution. Okay, put s square as y, right, any variable. So this becomes 2y square plus 12y plus 16 equal to 0. Now it's a quadratic equation, you can find out what is y. Okay, use a calculator, get the values. Y, a square as a y, every s square is y. Okay, once I get a y, I can substitute a square once again and find out the 2 more roots. Okay, this is minus 2 and minus 4, right? So now I come to know that what is y? Y is s square. So I have an option, a square is minus 2 or s square is minus 4. Correct? So what is s? S is equal to plus or minus. The minus becomes a j now. This is root 2, or s is equal to plus or minus j, root of 4 is 2. So you see you have 4 roots on the y-axis. That's the answer. Right? Straightforward. So, so number of roots on the imaginary axis or number of poles present on the imaginary axis is equal to 4 here.